first of all, my name is Antonello Scardicchio. I will be teaching the first part of this class, which is on statistical mechanics. So the class will essentially cover three main topics. The first part, which will take 10 lectures, we hope no more than that, will be a recap on thermodynamics. The second part will be a part on random variables and statistics. And the third part will be on proper statistical mechanics. Okay. So I will be teaching thermodynamics and then the first part of the random variables part, and then the second part of the class. So this will be a total of 15 lectures, the first part. The second 15 lectures will be taught by Matteo Marsili. Okay. We are both in the condensed matter and statistical mechanics group, so we are experts on this thing. You can ask very difficult questions. I'm joking. So, our offices are both on the second floor, so whenever you have a question, you can come. And there will be a teaching assistant, although his or her name has not been decided yet. So we'll tell you more about this maybe tomorrow. And the other thing that I need to tell you is that the class will be actually, as you know, I mean, the first 15 lectures will be from now until the end of April, and then the other 15 lectures will be later on in, I don't remember when, June, July, something. June. Okay, so. All right. So, for what concerns books, for this first part, since it's a recap, so I'm just going over things that I assume you have already seen in this form or a very similar form, and I will actually I will try to give it more of a flavor which is similar to the things that we will see in the second part of the course. So any book on thermodynamics is essentially good. Okay, so my reference is Fermi's lectures on thermodynamics. Which is a course that Enrico Fermi taught at Columbia University in summer of some year in the 30s, I don't remember. So, and it's pretty formal, it's pretty self-consistent, and if you already know the subject, and you should already know the subject, it's a very good reference. Okay? Enrico Fermi, I think it's just called thermodynamics. But as I said, any book on thermodynamics will be fine. Even if you decide, I don't know which book you've used for your undergrad, Halliday Resnick or Feynman's lectures, or Landau Lifshitz if your class was very difficult. So anything will be fine. Okay. So so first of all, a historical note. thermodynamics was not invented by physicists, okay? If you look at all the names of the people that, that invented thermodynamics, essentially none of them were physicists. They were engineers. There was even somebody who was a surgeon in the army. So, you know, the most disparate of curricula, the more diverse curricula. And Joule, for example, was, I think was like homeschooled. He was somebody who was not even had been in college. Okay, so this was because at the time, just to tell you two things. First of all, the thermodynamics really concerns things which are concepts which occur in everyday, in our everyday experience. Okay, engineers were actually interested in understanding how steam engines worked. Okay, because they had invented steam engines, they had perfected steam engines, and they wanted to understand on a quantitative level how to make them better. Okay? And so, for example, Carnot treatise is on steam engines, starts from the concept of steam engines. And, and the second, and the other thing is just something to keep in mind for you, that because at the time, we are talking about the middle of the 1800s, so 1830s, 1850s, up to statistical mechanics was actually, you know, the logical consequence of, now we see it as a logical consequence of thermodynamics, and it was at the end of the 1800s, was understood towards the end of the 1800s. So at the times there was physics, right? People were doing physics. Physics was started with Galileo, then Newton. It's like 200 years before. And so what were physicists doing at the time? Well, they were doing other things. They thought they understood everything. They didn't care about what it was, and they thought it was just a, you know, a small detail to work it out. We really don't, you know, we really don't care. So they were doing, you know, things like studying the very fine details of three-body, what's called the three-body problem in the sky. So when you have three bodies which interact through gravitational forces, and they have, you know, their trajectories can be very, very complicated. And so the whole mathematical theory of this thing could actually be, you know, was actually the thing that was interesting physicists at the time. And engineers, and that, I have to say, that didn't lead to much of an understanding as thermodynamics did. So sometimes, you know, when you think about concrete problems and things that you want to make work better, you understand a lot of science and of physics. Okay. All right. So okay, so the first concept that we will need in order to talk about thermodynamics. So the first thing that I will tell you, and I'm already telling you this ahead because I'm assuming you know these things, so I'm not just jumping ahead and you don't have the background. I will be talking about the three laws of thermodynamics. Okay? So the first law is about, who knows? Temperature. Okay. Well, okay, maybe then I should go back to the Zeroth Law of Thermodynamics, because that's about temperature. Okay, let's do that. Let's discuss Zeroth Law. So actually, the laws of thermodynamics are 4, 1 plus 3. Okay, the Zeroth Law of Thermodynamics. What's the Zeroth Law of Thermodynamics? which has to do with temperature, as your friend has suggested.
We have, for instance, two systems, A and B.
Yes.
And if they are in equilibrium,
Mm-hmm.
and if B and C are interlocked, and then A and C are like they have the same temperature.
Okay, it's there in some form, but we have to clarify it a little bit. Okay, first of all, let's introduce the concept of temperature. If you take two bodies and put them in thermal contact with each other, which means that they can exchange heat, okay, the final result of this process will be that the temperature of the two bodies will be the same. So if I plot in time temperature of body A, let's say it's the hottest of the two. It starts from some value and goes down. If I plot the temperature of body B, it starts from some value, TB, and goes up. Okay, well, actually, the difference will never be really zero, but it will become smaller and smaller as time goes on. Okay. So at a certain point, it will be below any precision that we can actually measure, any precision of our measurement apparatus, thermometers. And, and therefore, the two bodies put together reach an equilibrium state in which the temperature is equal. Not only, but your friend here said that if we have a body A, body B, and they are in equilibrium with each other, okay, and if a body C, which is in equilibrium with body B, it will also be in equilibrium, thermal equilibrium with body A. Okay? So if you have ever seen in mathematics the concept of equivalence relation, this is the transitivity properties. If A is equal to B, B is equal to C, then A is equal to C. Here we have an equality signs between thermodynamic objects. Okay. So, very good. So let's now consider.
So do we have conclusions on cases in which Zeroth law fails?
So the question is if we have cases in which the first law, the zeroth law fails, and the answer is as far as the bodies are sufficiently big, like they are composed of sufficiently big number of particles, that never happens. Okay, this is the same. You know, this has the same status. I think it's actually, you know, it's even on a better footing than the second law that you guys know, the one about increasing of entropy. If we are talking about macroscopic bodies, namely bodies with a lot of particles, like for example, the number of particles and the number of atoms or molecules in air in this room is of order of 10 to the 23, 10 to the 24. That's a big number. Okay, it's really, really a big number. It's bigger than Italian debts. So, and so we will see in statistical mechanics how this number actually, why these numbers so big actually lead to no violations of this law. Okay, so statistical mechanics will be a justification of these laws, and you will see that under appropriate hypotheses, which are essentially verified always, always verified for macroscopic bodies, then you will there is no violation to these laws. Of course, if you are talking about two particles, okay, if body A is a billiard ball and body B is a billiard ball, why should this law? What you have to keep in mind is steam engines, you know, the engine of your car or of your scooter or the air in the room. Okay, this is the things that thermodynamics is set up to explain. Okay, very good. So okay, let me. Yes.
Can this law be applied on two galaxies?
Well, this law, the question is whether this law can be applied in cosmological settings. Okay, in the sense, you asked about two galaxies. Thermodynamics works very well for cosmological settings. For example, for the interstellar gas, for describing the core of stars. So it's not a problem that it holds on Earth and not up in the sky. But usually galaxies do not interact, right? And the question is, if I take a galaxy and put another close in contact to another galaxy, what does it mean? I mean, they have to really interact. They have to exchange heat. So, in principle, if you imagine all the stars colliding with each other, then it holds. But this is a very extreme situation. I think you cannot speak of galaxies when you talk about this thing. Okay, so let's go on. So the first law introduces the concept of internal energy. So consider a piston full of hot gas. Okay, there is a gas inside the piston. And now we know that gas is composed of molecules that they go around in very high velocities, with very high speeds, and they bump on the walls and so on and so forth. But we don't see molecules with our naked eyes. Okay, so when thermodynamics was set up, there was not this concept of a gas. Okay. So this is something that came up later with the hypothesis of Boltzmann and Maxwell, and then was tested, many, many times. Now we know it's true. But you have to just imagine this thing, which is there is hot gas inside here. And this piston is held tightly, and then it's moved a little bit. It's allowed to move a little bit. So the gas is hot and wants to expand. It moves by a distance dh, and it makes some work, dW, which is the pressure of the gas times S, the surface of the piston, times dH. Now, this symbol means, as you know, differential. Okay, a very small quantity. There's actually a very well defined mathematical sense in which this quantity is small, and so on and so forth. And this is a differential because you can measure. You have this function height, and if you take the differential between two situations, very very close to each other, you get an exact differential dH. I put a bar on this dW, and this is more or less common use, okay? Just to stress that the work done is very small, in the sense that when dH goes to 0, it goes to 0. But it's not an exact differential in mathematics. So there is no function that we take the derivatives of, and it gives us the work of the body. Okay? So this is the work done by the system. So if there is work done, in classical mechanics, anyway, even quantum mechanics, if there is work done, we think about that there must be some form of energy which is transformed. Is it potential energy? Is it kinetic energy? Well, not really. I mean, the gas was, I mean, the center of mass of the gas did not move much, moved by delta H. So it cannot be potential energy, gravitational potential energy, because this thing is, you know, there is no G here. There's no, if you do the same experiment on the moon, you get the same. If it's the same gas at the same temperature, you get the same work out. So it can't be gravitational. So any energy, the energy of the gas, which is neither potential nor kinetic, it was called, and it is still called, internal energy. Okay? And if this is the work done by the system, and the system is completely, the system meaning the gas, okay? And it is completely, if this piston is completely isolated from the outside, such that there is no heat transfer, there is nothing, so this work has to come from somewhere, okay? And so we write that since this is the work done by the system, not on the system, it must cost some energy to the system. The energy of the system goes down. The internal energy of the system goes down. So we put a minus T. Okay? Mm-hmm.
When you were saying that there is not a change with the external.
No, I'm assuming there is no exchange.
It's just that W should be equal to 0 because it will be adiabatic.
What you want to be 0?
If there is not the change of energy with the external U, so this means this work should be equal to 0.
No. Because the work, no, so you're saying if this work should be 0 because there is no heat exchange with the environment. No. The work is not 0 because I'm putting a force on the piston, and the gas is counteracting this force. Okay, so it makes a work. So you can think about this as being, I don't know, there is a pulley here, something that then brings, when this goes up, okay, brings up. Well, there is a series of pulleys, okay. So this brings up some weight. So you're really doing some work, physical work. The gas has done physical work without taking anything from the environment, okay? If we take something from the environment, we have to add it to this equation, okay? Now, suppose we have the same situation, and now, as your friend suggests, let's assume that the environment is giving some heat. Okay, so I don't know, we put some fire over here. Sorry, my depiction of fire is not the best. So we put some fire, and we know that the fire gives some heat, some form of energy to the gas, and the gas then does some work. And we assume that we can just sum these two things. So first, there is a lot behind this law, okay? First of all, because work is usually measured in joules, you know, Newton per meters, or any other reference, other units of measure that you want in the international system. And heat is measured in calories, okay? If you go and look at your your natural gas bill, okay, it tells you that you have used so many calories and you have to pay so many euros or dollars. Okay, they don't tell you have used so many joules. Okay, so this is you know, the fact that we can sum them. You cannot sum apples and oranges, right? When you sum things, it means that they have the same unit of measure. Okay? They are the same thing. So the fact that we can sum heat and work with a minus sign, but that doesn't matter because it's the definition of work we have used, the work done by the system, while the heat is the heat absorbed by the system. It means that they are the same thing. And in fact, this was a great discovery by Joule. Okay? And the experiment that he did, you probably know this. Have you ever? Yeah, he did two experiments actually. The first one was more precise, but the second one is clearer. Do you know which experiment? How did he show that work and calories are the same? Have you ever heard about the experiment with the paddles? So yeah, the bucket of water, okay, thermally isolated from the environment, and then he put in some paddles. There was a crank. And he started turning the crank in a controlled way, okay? So in a way in which he could actually control how much work he was doing on the crank. And the paddles went around. So this thing, this is my depiction of paddles. Like, you know, these things rotate around, okay? The water started moving, but exerted friction on the paddle. So you know, it requires some strength to go with the paddles. And you keep doing that, and in the end, the water is isolated from the environment. Remember this. In the end, you have done some work. Okay? Where did that work go? Heat. But how can you measure that it went into heat? Because water becomes hotter. If you put a thermometer in, temperature went high. So work was transferred into heat. Work and heat are the same thing. And in fact, 1 calorie is 4.18 joules. Okay? What's the definition of calorie? To increase the temperature of what?
1 gram of
1 gram of
from
water?
14.5 to 15.5 degrees centigrade.
Okay, very good. Why not 16.5 and 17.5?
I'm not sure, but maybe
have some reason, I think. Maybe, I don't know. Or maybe it is the temperature that is available something.
Okay, that's a good question. So the definition your friend gave is correct. It's actually very correct. Okay, that is correct and it's very correct. So it's correct because he said it's the energy which is needed to raise the temperature of 1 gram of water between 14.5 Celsius and 15.5 Celsius. There are several definitions of calories, actually. And this is one. Okay, now it's not an independent definition anymore. It's defined, if you go in the international system, you see that it's defined at 4.1840000 joules, and then everything relies on the definition of joules. It's just a concept. But this point is correct. This was the original definition. And in fact, if you do the experiment at higher temperatures, between, I don't know, 90.6 Celsius and 91.6 Celsius, you get a different value here. Why you get a different value? Because water changes, right? Water is about to, at 90 degrees Celsius, water is about to boil. So it's not going to be water anymore. It's going to be steam. So you have to be careful when you do this thing. Yeah? And then matter is, usually we work with small variations of temperature. Like things around us don't melt, don't do, I mean, you seldom see concrete melting or, you know, things because it's too hot outside. But you have to take into account that the state of matter change. So in thermodynamics, saying, you know, at which temperature you're doing your experiment is important. All right, very good. So the first law says that du is an exact differential. Okay? So this means that the change in internal energy let's consider a state of gas, okay? We have been talking about water, but water is a bit too complicated for us. So let's talk about ideal gases, which is the simplest situation in the world. It means that you go between point A and point B with different paths, and you integrate you get only a function of B and A independent of the path. Separately, dq and dw don't have this. They don't have this property. Okay. So this means that heat exchange and work done are some concepts which are useful, okay, that we can measure, but they do not describe the internal state of our gas. What describes the internal state of our gas is the internal energy. So let me make an example. So for examples, we will use ideal gases because they are very simple, because they have a very simple equation of state, because they have of many, many properties. Okay? But can you make me an example of an ideal gas? Air, is it an ideal gas? you cannot make me an example of ideal gas because ideal gases don't exist. Okay? They are very good idealization. That's why they are called ideal. Okay? You can take a real gas and go to very high temperature, and that behaves very well like an ideal gas. That's what you were going to say. Yes, I knew it. I just wanted to stress that in practice, there is no gas which behaves like an ideal gas throughout all the temperature range. Okay? All gases liquefy when you go sufficiently close to zero. Okay? And although when you go sufficiently close to zero, things become a little bit complicated because quantum mechanics start playing a very important role. And if you go to sufficiently high temperatures, essentially all gases behave like ideal gases. So all gases are ideal gases, and no gas is an ideal gas, depending where you are in temperature. So, first of all, we have an equation of state for the ideal gas that we can actually write down exactly. And the equation of state for the ideal gas is PV. Okay, very good. So N kBT. And N is the number of particles, T is the temperature, V is the volume, P is the pressure, and Kb is a constant, which is called Boltzmann's constant, whose value is, before I look it down, okay, 1.38 times 10 to the minus 23. That's 23? Yes. And the units of measures are joules over Kelvin. Not mole, because here I didn't say number of moles. I said number of particles. Okay. That's R. That's what he was saying. R. Okay, R you have to multiply by particles per mole. Blah, blah, blah. Oh, and notice that Celsius goes with a degree, and Kelvin does not go with a degree. If you put Kelvin with degree, you fail the exam. No, I'm joking. It's a big mistake, okay? Okay. So do you know the difference between intensive and extensive variable? Is P intensive variable or extensive? Intensive. What does intensive mean? The extensive ones are add up, the intensive ones okay, right. Okay, so if I increase the number of if I double the number of particles, the extensive quantities double. Okay. So when you have an equation, one check that you want in thermodynamics, in statistical mechanics is exactly the same. One thing you want to check is that the number of intensive and extensive variables are the same on both sides. Because if it is an equation, if I double the number of particles, both the left-hand side and the right-hand side have to double. Otherwise, it's not an equation. Okay? And in fact, here we have intensive, extensive. And here, temperature is intensive. And where is the extensive? N. Okay? If I double the number of particles, double the volume. I take 2 here and 2 here. This doesn't change. This doesn't change. Just a check for, when you find an equation you want to find if it is correct or not, the first thing you have to check is the unit of measure. And the second thing you have to check is, in thermodynamics you have this trick, you can check if the number of extensive variables, number of intensive variables. Okay.
Why they introduced these two things, intensive and extensive?
Sorry, say it again.
Why they introduced these two things, these two concepts?
Oh, because they are very useful. No, because pressure is really intensive, right? And temperature is really intensive. I mean, it helps you think about the thing. In fact, some books, I mean, now modern books don't do it anymore, but old books used to write intensive variables with small letters and extensive variables with large letter. So this would be something like PV is equal to NKBT. They don't do it anymore. But you have to keep it in mind. Okay, so let's introduce the concept of a reversible transformation. A reversible transformation is a transformation between a state of your system A, which in this case is, we can say TA, BA. The ideal gases in general, but in this particular case, ideal gases are defined by three variables: pressure, volume, and temperature. But there is an equation between them, which is this, okay? The equation of state. So three variables, one equation means we have two free variables. So if I define a state of my system, I can either define it in terms of pressure and volume, or pressure and temperature, or temperature and volume, and find the other one. Okay? And I have, so a reversible transformation, as I said, is a transformation between two states of my system, which is done through equilibrium states. So at all points in this transformation, the equation of state is verified. This is a reversible transformation, okay? This is a reversible transformation. This is a reversible transformation. Okay, although this is quite crazy, it doesn't matter. The important thing is that at every point here, I have point, I don't know, TC, it's C, I have TC, VC, and they satisfy TC, VC, and PC, which is they satisfy this equation. Okay, so okay, so very good. So the idea is that if I take du and I integrate over this path or over this path, it's going to give me the same result. Okay. So for example, okay, now the diagram became complicated. Did you write it down? Let's assume that state A and state B have the same temperature. Okay, and let's put an isotherm. So let's do an isothermal transformation between them. So what is the work done? The work done is the integral of dW between A and B on when I integrate the work, I need to specify which path I take. It's not like the internal energy. This is the meaning of the internal energy. For internal energy, you can take any path. Okay, the one that simplifies your calculation. So we'll do this kind of calculations many times in class, and you're supposed to be extreme at the end. Actually the beginning of the class, but certainly by half of it, you're supposed to be very good at this, because these things are everywhere when we start talking about statistical mechanics. PDV. So if I want to do this integral now, what should I use? I said it's a reversible isothermal transformation. We can use the equation of state. Okay? So the equation of state states that P is N KB T over V. And now we use the fact that T is constant. Oh, sorry, dV. T is constant, so we take it out. And N and KB are also constant. Now, suppose we want to get the heat exchanged by the system in this transformation. What can we use? Now we have to really use the fact that this is an ideal gas. Well, okay, we actually used it already because we used the equation of state. But there's one property of the ideal gases which is quite interesting. And it's essentially the defining properties of ideal gases. And it's that the internal energy of an ideal gas, no, that this is conserved, it's always true. That's the first law we are just discussing. Okay? It's only a function of temperature. Okay? This was also a discovery of Joule. The experiment was the following. And you put a thermometer here. So you have some gas in the container A, and this is, there is water here or whatever. I mean, and everything is isolated from the environment. Okay. So you have gas in the container A, and then at a certain point you open here, and gas goes into the container B. So the volume doubles. Okay? So if the energy is a function of the gas is a function of the volume, it means that in order to then it has to equilibrate with the exterior, right? And equilibration means that if this energy changed, the total energy has to be conserved because it's completely isolated from exteriors and no work is done. Okay? So this means that it has to either take or give a little bit of energy to the water. And so the temperature of the water has to change. And Joule actually observed very, very small changes in temperature. And therefore he argued that for an ideal gas, there should be no change in temperature. So it means that the internal energy of the gas, when expanded from A to B, without doing any work, did not change. Okay, so the internal energy of the gas is only a function of the temperature. And therefore, the internal energy change along this between point A and point B is what? Is 0. Because TB is equal to TA. Okay. So the heat absorbed by the system is equal to V, not minus V, because we have Q minus V. Okay, so the heat absorbed by the gas is the same. The work is not negative because the system is expanding. This is the work done by the system. Okay? You have a piston, the piston goes up. The work is positive. If I was going the other direction, the work will be negative. And the heat absorbed will be negative. Okay? Because what happens? If you compress your system, okay, you're giving it energy, but then we say that the temperature is constant. So the system cannot keep this energy because the internal energy is proportional to the temperature. So it has to give it away. So gives heat. Okay? And since this transformation is reversible, the work and heat exchange are the same in both directions. Okay? So the internal energy of an ideal gas, we said it's proportional to the temperature. The constant of proportionality is called CV. And then there is a constant here, an additive constant on which we cannot say anything because we can only measure differences of energies. This has to do with things that occur at zero, at absolute zero. So quantum mechanics and kicks in, and things become more complicated. So, but for our small project of understanding thermodynamics, this is just a constant. We don't care about it. For example, it depends really on the statistics of your particle. So if you know what's the difference between fermions and bosons, that we will see at the end of the class, you will see with Professor Marcia at the end of the class, this energy depends a lot whether your particles are bosons or fermions. Okay? Because if it is bosons, you can actually go down a lot because you can feel, if you have your ground state, you have done quantum mechanics, so you know this thing. If you have your ground states, you can put all the particles in the ground states. If it is fermions, then you have to fill up to a certain level, and so this thing is higher. In fact, when we talk about fermions at room temperature, this thing here is much bigger than this. Well, it's not linear for fermions, but the temperature-dependent part is very, very small. So you can assume that even at room temperature, you are at zero temperature for fermions. For bosons, you can absolutely not do that. OK, very good. So this is an example of what to do. OK. Let's, all right, so first of all, you will see this with the tutor in the exercises and problems that you will do, and you will see that sometimes the kind of work which is done is not just PDV. It depends on your system. You can do magnetic work. You can do electric work. Okay, your system can do electric work. You can do all sorts of work. Whatever the kind of work that it is, it goes in internal energy together with heat absorbed by the system. Okay, so sometimes, for example, a magnet does a lot of work. Oh, for example, you know why you heard last year LHC had to stop working for a while. LHC is this big accelerator which is down in the Swiss mountains. It's actually underground. Okay, so the problem there was the following: they had these superconducting gigantic magnets. They're really gigantic. Like, I don't know. It's probably the radius is like something like 6 meters. Okay. So that people walk in them. Okay, and so they when they turn them off. So when they are on, there is electricity and there is this big magnetic fields that they have to confine the particles that pass in, and then you turn them off, and then the first law tells you that the work that you are doing on the system is actually transforming itself into heat, and this thing heated a lot. Of course, everything was calculated because people, these people that did that things know physics, but there was a slight miscalculation. So this thing heated too much, and a couple of, I don't remember. It was some connections just melted. Okay. So that was an example. This was an example. I just wanted to give you an example. I gave you a messy story. Just go and read it on the New York Times. So it's explained. It's explained online very well. Or we can ask some of our colleagues which actually worked there to explain it better to you. So, but this is just to say that no work was done in terms of PDV, but work was done in terms of BDM, where M is the magnetization of the system. And this was transformed into heat, and this caused a big trouble. Then LHC had to stop for like 6 months to repair this thing. So you have to really be careful about these things. Okay, so before we talk about the second law, I want to tell you a little bit about one particular cycle which is Carnot cycle. So first of all, we are going to talk about the second law now. Now you have all read about the second law. You all know about the second law for sure. Even if you were journalists and not physicists, you would have heard about the second law. Okay? So what's the second law? What does it say? Anybody? The entropy of the system always increases. Okay, this is the intuitive notion. Yes, we have to be more careful. But that's correct, with a few caveats. There are several...
limit on the energy, on the work that we do.
It's also a limit on the work that we do. That's correct. Because it says that in a cycle, it is impossible in the cycle that the only effect is that of taking taking heat and transforming it into work. So it clearly is a limitation on the work that we can do. For example, is a limitation in the efficiency of things. Okay? Because it means that there is also a little bit of energy that goes into heat someplace. Okay? And you cannot really use it. We have to introduce the concept of entropy. Once we introduce the concept of entropy, we can show that this is equivalent. The two formulations are equivalent. So what I just said is equivalent to say that the entropy the entropy is a state function. Okay, so it will be like the energy. So in a reversible cycle, the entropy does not change of the system. Okay, but if there is heat exchange with the environment, then the entropy will go up. So but let not me just tell you things which I will tell you anyway, either this class or the next. Okay, let's consider Carnot cycle. Again, let's take our favorite system, which is the ideal gas. And let's do an isothermal transformation between A and B, an adiabatic transformation between B and C. Adiabatic means that the system is isolated from the exterior, from the environment. Okay? So whatever work is done at the expense of internal energy, not at the expense of external heat which comes in. And then we go back. We compress the system. Okay? And then we adiabatically force it to go back to A. First of all, without knowing anything, is the work done by the system positive or negative? What do you think? 0? No. Positive. Okay. Why? Why did you say positive? Because it's the area, right? The work done by the system is the area enclosed in the PV diagram. Oh, this is only true with the PV diagram. If I put PT, don't dare to write integral P dt equal work. Okay? You fail the exam. There are many ways of failing the exam. I hope I can tell you all of them before the end of the class. So, since the area is positive here, then the work done is positive. If I reverse the cycle, if the cycle goes the other direction, then nothing changes. The work is still positive. So I run a motor, and I get positive work. I run the motor in the opposite, doing work on the wheels and getting things out, and the work is still positive. No, the work is negative. In fact, if you do the integral in the other direction, dV is negative, right? When I integrate P dV here, this is negative, and P is higher here. So in fact, the negative work done is the other.
It depends on the path, right? It depends on the path.
On the what? On the path. Yeah, no, the same path. I'm just saying, if I reverse it, if I go in the other direction, if I do the path in the other direction, this means reversing the process. It means that instead of going from A to B, I go from B to A, then A to D, then D to C, and back. So, but for the moment, let's consider the, oops, I erased the wrong arrows. Let's consider this work, okay? So the work done is positive. And the heat absorbed, is it positive or negative? Is what? It's negative. You still have in mind different. You have Q plus V W inside, right? It's minus dW. You always have in mind the other sign, yes. Because I'm sorry, since you come from different schools, I have to apologize, but in the world of physics, I mean, people decide to use different notations. dq plus dW, dq minus dW. Some people call WL. Some people call the internal energy U. Others call them other things. I'm sorry. I mean, you have to have an internal routine that adjusts everything that I say in things that you've learned, or vice versa. Everything that you have learned in the terminology that I'm using. Okay. Why is it 0? It's a constant between what and what? I say on the entire cycle. On the top. No, I'm not talking about only the top. I'm talking about the entire cycle. So AB plus BC plus CD plus DA. They change. Why? Because, by definition, because it's a state function, right? It only depends on the state. Doesn't matter which path we take. Okay? This is important. So this is not true only for ideal gases. If you do the same kind of cycle with a non-ideal gas, the work change, the heat exchange change, but the energy is always to be 0. The change in energy is always to be 0. Okay? Keep this in mind. This is a universe. This is the first law. Doesn't matter which object is doing the job. If it's doing a cycle and comes back, it's the change in internal energy is going to be 0. Okay. So let's look at, as I say, du is equal to 0. But as our friend has said, it's correct. The integral between A and B in du is equal to 0, because this is an isotherm. And also the integral between C and D for the same reason. So the change between B and C of internal energy has to be equal to the change between D and A of the internal energy, because all the changes have to sum to 0. So the work done on the AB branch is equal to the heat absorbed in the AB branch, and it's equal to, you do the same calculation as before, you find T1 logarithm of VB divided by VA. Okay. On the CD branch, you find the same thing. VD over VC, sorry. It's always the final over the initial, but since VD is less than VC, now this is going to be negative, because logarithm of something smaller than 1 is that. In the adiabatic branch, we say that there is no heat exchange with the exterior, so dq is equal to 0. Okay? But dq is du plus dw. Okay? du is cv dt plus dw, and dw is pdv. Equal to 0. But remember, this is a reversible process, so we can take T from the equation of state. Okay? So this is CV. And KB. Oh, sorry. The T, yeah. So T is PV over nkbt, nkb. Okay, so this becomes 1 divided by n kb. Yeah, maybe I wanted to do something different. Okay, let's do this.
PdV plus dP would be
Yeah, I have to take the differential of the product, which is the sum of the choosing. Yeah, I was just, sorry, I was thinking about something else. Plus P dV is equal to 0. Okay, so this is P. So just to simplify things, you know what CV is for an ideal gas? For I said an ideal gas, I need to specify it better. You said 3½ nkb, right? R is nkb. Okay. This is correct for an ideal gas, which is also monoatomic. Okay. If you have a diatomic gas, it's 5 halves, something like that. So let's assume this is a monoatomic. It's a simple situation. 3½ nkb. So instead of this ugly number, I can write 3½. So 3½ plus 1 P dV plus V dP is equal to 0. Okay. So this means that PV to the 5½ is equal to 0. Okay, and in fact, this is the equation the equation of state along an adiabatic. PV to the 5½ is a constant. That 5½ is usually called gamma, small gamma, but for the moment, let's just keep it. Oh, sorry. I'd forgotten this because this is 3½ but this is this piece here. Sorry. In fact, it sounds strange, 5½ It should be 5/3. So. Okay? Why is this? So let me do it more explicit. So this becomes dP V to the 5/3 plus P dV to the 5/3 is equal to 0. Okay? Now V to the dV 5/3 is 5/3 V to the 5/3 minus 1 times dV. Okay, and then I cross V to the 5/3 multiply by V, and I find the same equation. So PV to the gamma is equal to a constant on the BC branch and on the AD branch, which means that if I want to trade P for T, which means that TV to the gamma minus 1 is equal to a constant, actually another constant prime, doesn't really matter. Okay, so from this equation, we find that the logarithm of T1 over T2 is equal to the logarithm of Vc over Vb is equal to the logarithm of, because now we apply it over on the other side, is equal to the logarithm of Va over Vd. Now, let's get rid of this for a second. Question? Why is it what? Sorry? Mm-hmm. Where? No, because this is 5. Okay, so let me write this. So first of all, you have to do this calculation by yourself at home. When you go home, you take your lecture notes, you go over it, you find all the mistakes that I've done, which will be non-zero. Okay. So, but in this case, I think I'm pretty confident because this is 5/2. Okay. So just remove the half. This becomes 5 and 3, and here you get 5/3. Okay. So you have to do the calculation by yourself at home, you know, in your room, sitting, or if the weather is nice on the terrace, you see, you look at the sea. So, no, you joke, but it's actually inspirational to look at the sea while you do physics. Look and you can see very far. So, okay, now I want to calculate the efficiency. Okay. What's the efficiency? The efficiency of this engine or this cycle. An engine is a cycle, right? Because when you turn off the car, it's in the same state as when you took it out from the garage, more or less. Okay, so it's a big cycle in which many things happen, but in the end, your car is supposed to. The engine of your car is supposed to be in the same state where it started. Of course, this is not, because the engine of the car eats up, also. But if you think, I mean, an engine of a car does thousands of cycles per minute. Okay, these rounds per minute. So the second thing you see on your car, there's a tachymeter, and then there is this thing that measures the rounds per minute. So you do thousands of rounds per minute, and the temperature of the engine of the car only goes up, I don't know, like 90 degrees Celsius. Okay, so if you divide that per cycle, you see that actually each cycle is a very good approximation that nothing happened. There was no heat exchange with the exterior and so on. But, okay, so the efficiency is the work done divided by the heat absorbed, only the part of the heat which is absorbed. What is the heat absorbed? Just a second. In which branch of this cycle is heat absorbed? You say A, B. Anybody agrees or disagrees? CD. Why CD? And so? Are we doing work on the system, or is the system doing work for us? We are doing work on the system. If you are doing work at constant temperature, the internal energy is constant because it's constant temperature. So we have to take out energy from the system. So energy, heat is released from the system. So where is so on the BC branch, it's adiabatic. There is no heat exchange by definition. On the AD branch, the A branch is the same, so only AB. So our friend was correct. So in the AB branch, the system is doing work for us at constant temperature, so we have to provide heat. Okay? So the efficiency will be the entire work done by the system divided by the heat absorbed. Let me call it QAB. Okay, we calculated. Now the work done is equal to no. So you can find it in two ways. Okay, either you calculate the area of this thing, which means that you have to do this integral, then you have to do this integral, then subtract this integral and this integral here, or there is a smarter way to do it. Do you have an idea?
No, I want to know something.
Ah, okay.
dq is positive, no?
What? Sorry?
Q is positive.
Yeah.
But
This is the heat absorbed by the system. Okay?
it should be negative.
Why should be negative?
He lost, no?
Is work positive or negative?
No, the work is positive.
The work is positive. The internal energy, is it positive or negative? Or zero?
Zero.
Zero. So it's Q minus W, which is zero. So if W is positive, Q is positive.
Maybe another way. Just to replace W, we have Q is U plus W, right?
Yes?
And then we replace for W, Q minus U.
Yes. And U is?
And it's just the difference in temperature.
And the entire cycle is?
Oh, 0.
The work done in the entire cycle is is Q minus U. But so the total heat exchanged and exchange means absorbed minus given away, plus the change in energy, internal energy. But since it is a cycle, the internal energy is zero. Change in internal energy is zero. So I can just put here QAB plus QCD. And then if you now, if you now take these things here, and right, and you do two steps, you find that this is equal to 1 minus T2 divided by T1.
And I think this one is plus, right? 1 plus QCD over QAB.
Right. It's QCD which is negative, so you're right. Very good question. So next lecture, I want to see some of you doing this calculation. I mean, I gave you all the ingredients here, okay? It's just a little bit of algebra. It's 2 steps of algebra. I don't want to do it on the blackboard because we are already over time, okay? So it's 2 steps of algebra. I told you about this relation here, and you have to use it to get this result here. Okay, so just one thing. Another thing that you can actually see here is that QAB. I want you to check the following thing: QAB plus divided by T1 plus QCD divided by T2 is equal to 0. And we'll discuss this next next lecture. So for homework, you have to do the 3 steps of algebra that bring you to this relation here. And moreover, verify that this is true. And this is just one step, very easy. Probably you have already seen it. And then we'll talk about entropy tomorrow. OK? Thank you.